Okay. So we talked about how logs are exponents. So we use log equals exponent. And we're going back and forth. The base of the log is the base of the exponent. Now, we also said that our logs for our log key works in base 10. If we have any other base, it functions the same way as a base 10 log, but we can't put it in your calculator unless we change the base. So we took a look at where your change of base key was and how the other ways to get around it. So we looked at this on Friday. We found that our logs will make a nice little graph. Here's our exponential graphs. Our log graphs go like this.
Where is that?
This was from Friday. I'm just recapping what we did on Friday in case it's been so long that we're really not sure. Now, this is a reflection in the line y equals x. Because your rule for your reflection is that you interchange the x and the y. This is why this is the inverse. The inverse is a reflection over your y equals x line. And we did this when we did parabolas. We did this when we did some other functions. Sometimes we had to limit your domain to give us a true inverse. But this works very nicely. Where this point is the 0, 1, this point is the 1, 0. Or it's a little bit off. So we talked about this on Friday. Everybody okay with this? Business. Then we also looked at some properties. We said we'll get to learn these properties a little bit. We can find a lot of them ourselves. The LNEs are nice because the LNE cancels itself out. 1 equals 1. We talked about some of your properties. And that's probably about as far as we got. Without you whining. Nope, we did this. We did this together. We talked about the graph, how we put this into your exponential equation. Then we interchange these. This was our 1/2, this was our 1, 2, and 4, and we swap these around. And this is your point that you're going to find, your 2, 1, and your 4, 2. And we said, here's your log graph. The domain and the range also interchange. So when the domain of your exponential function was all real numbers, that becomes the range of this guy. When the range of your exponential curve was 0 and greater, that becomes this guy's domain. Okay, and we looked at this point, the 1, 0 point being a common point off your core graphs without any transformations. Sound familiar? We did this on Friday, right? And I think that's about as far as we got. We're going to work a lot more with logs to see that they are inverses. The one reason that we use logs is because when we're solving like your applications and you have a variable in the exponent, the only way without graphing it to solve it algebraically is to use a log to bring that variable down. That is one of the best reasons we use logs for. Science uses logs a lot. I think chemistry? No? Physics? Physics. Am I taking physics? No? Yeah, I think physics. One of them uses logs a lot. No logs. Okay, now, I gave you a list of the log transformation rules. They look exactly like the old transformation rules, everything we've done. If I had this, here was my core graph for a squaring function, the quadratic, right? And it went like this. If I moved it inside, it moved it horizontally the opposite way. The logs work the same way. When you move it inside, it goes horizontally the opposite way. It does the same thing. What happens is we got the log word out there. So some kids get a little thrown off and don't realize they're the same exact transformations. If I did this, x squared minus 4, here's my vertical shift. Here's my vertical shift. using my log equation. It's just got to have a log out there. Okay, reflections. If we did this, let's put a negative out here, and we reflected it over, if the y is changed, we reflected it over the x-axis. We have the exact same thing here. And then if we put it next to the x, this one is a bad choice because it has no, it looks the same exact when you reflect it over the y-axis, but this is reflection over the y-axis. And we do the same thing here. So it really basically gives you the same transformations that we've used on all of our functions. They just look a little bit different with logs, so I printed them out, and you can kind of compare them off of that. And we'll do some so that you can see the difference. And a dilation. The dilation is your vertical stretch, your horizontal stretch, your shrink. If it's outside here, this C, we're stretching this if it's greater than 1. If it's less than 1, you're shrinking it. Now remember, when you stretch the parabola, it looked like it pulled it straight up, right? When you shrunk it, it looked like it flattened it out. So it kind of has that effect here. When it's inside, we call this a horizontal, opposite way. But we don't really use these as much as we use the one on the outside. So we'll take a look at those in a minute. All right, so just to kind of go through your rules so that you're comfortable with them. Now, we also have to look at your domain. Your domain for your basic log statement says 0 to infinity. So x has to be greater than 0. It cannot be equal to this. Whatever your x is. A good way to start is right in here. This has to follow your domain. X minus 1 has to be greater than 0. Domains are really helpful to go off of when you're using your logs. So this is going to be greater than 1. You can almost see where your shift is already, right? It went from here, just moved everything over 1. Your asymptotes move as well. In this one, this basic log function, this is your parent graph. What is your asymptote in this one? Which axis acts as a natural asymptote where it never crosses? The y. So your y-axis is your asymptote, and that's when x is equal to 0. Remember, our exponential one was down here when y was equal to 0. So because we interchanged them, the y went to the x. So x equals 0 is a natural asymptote. And remember with the exponential one, we kind of used that 0.01. Use the 0.10 to help you go back and forth. So now, if I'm going to take this, and it's a horizontal shift in the opposite direction, and move over 1. So this is going to become 2, 0. Everybody moves over 1. Where your x is equal to 0, your new asymptote is x is equal to 1. Everything moves 1 to the right with this. Your domain will not change this time because your domain is all real numbers. So your domain is not going to change. I'm sorry, your range is not going to change, not your domain. So your range is not going to change because you're all real numbers. We figured out our domain first, so we knew where our domain was. But your range has no effect right now. It's still all real numbers. Your asymptote moves, your graph moves. Good. Same thing we did with your exponential curves. You moved your asymptote, which was your y equals 0. We only move that if we had any vertical shifts. This kind of works the opposite way because everything is opposite. X is interchanged with y. So this time, the ones that affect the x are the ones that are going to affect the asymptote. Make sense? And you can absolutely graph this as well. Log base 10, you can just put in your calculator log x minus 1. Even if it was a base 2, you could still put base 10 in there. It just becomes a little sharper. Just like your other ones were a little sharper as the base is increased. But you can still do it that way. So we took a look at this, and you would end up with this graph. You can kind of see where you can't use any negatives in there. And you can even do a value on it and see if it would use 1. If you said x value 1, it's going to leave it blank because it can't use it. There's your asymptote right there. Good? I know you all didn't plan on working today, but it's not so bad. We're almost done. Now, here is a shift. If I want to write this, I might want to put it over here. Just like we did with your exponential ones. If it's easier to look on that side, just switch it. There's your commutative property when you add. You can swap them. So this gives me a vertical shift. Up 2 units. Now, we start with your basic log function. Always start with your core, your parent graph. Okay. Is your domain going to change in this if we're shifting vertical? No. So your domain is still the same. In this one, if we shift vertical, will your range change? So what will your new range be for this? Where's your range going? It's still going from here to infinity, right? So your range doesn't change on this one. Same thing when we did your exponential one. Remember when you did your exponential curves? Where was your exponential curve? If we did a vertical, our range changed, but our domain never changed. Okay, so it's kind of the opposite effect here. Alright? So your domain and your range are not changing. What's happening is you're moving this guy and use this point right here and shift this up to bring this x, this 1, 0 up to. You're changing your y. So now it's just coming from there. You can tell your domain didn't change and your range didn't change. What's your asymptote still? What would my asymptote be? X equals 0. Good. That's my y-axis. My x equals 0. We took a vertical shift up 2 units. That's all we did for this one. And now you can kind of get the feel of this. If I turn this around and I do this, I put a negative here. Here's my original log function. If I reflect this, my y is negating. So your y goes from positive to negative. Where's your reflection? Over the x-axis. So if you kind of keep track of this point, make this one over here go like this, and this one, if you continue your curve, is going to go like this. See it? There's your reflection over your x-axis. Your reflection over your y-axis, when the x is negative by itself, will be here. Will be this one. Okay. Make sense? No? It's just a reflection. If you're reflecting over the x-axis, do it a piece at a time. Do this piece first. It makes it easier. See that reflection? Now just continue your curve. That's this reflection. Like if you took this point, and you took this point, and you put it up over here. You took this point, and you put it up over here. That's your reflection. This reflection is probably easier to see over the y-axis. That was probably easier to look at. It looks like you're folded and seeing symmetry. This one's a little harder because you're crossing over your axis. All right? Do you have any questions about these? Basic?
So was that the number 2?
No, this was, I threw this in here.
Oh, okay.
Yeah,
Okay.
This we did, yeah, I'm sorry.
I
I probably confused you. This I just threw in for a reflection, because I don't think I have another one under there, do I?
No.
No, that was it. That was the last one, right? I just wanted to throw a reflection in here. So,
Is this log x to the 1?
This one was log x. Yeah, I just this was your basic log, and I put a negative in front of here, and then I switched and put a negative in front of the x.
Oh, okay.
Yeah, just to kind of show you how the negatives work, how the logs work. We have time? All right, we have a couple minutes. Now, your domains work right off of your transformations. Your ln's work the same as your logs. They are also logs. So your parent graph for this would just be ln x. They work just like a log. Remember we looked at it. Because your base e works just like an exponent of a 2 base or 3 base. Same thing. Now, this says you're going to shift it which way? To the right. So this point right here is just going to the right 2 places. So it's now at 3, 0. My asymptote, which was x equals 0, is now going to the right 2 places, which is x equals 2. Everything's shifted. Horizontally it's shifted. Now, we could do the same thing we did before. Your original domain for this red one said 0, 0 to infinity. X has to be greater than 0. So you can take this out and say, make this greater than 0. So now, my new domain has to be 2 to infinity. And it has to stay a soft bracket because you can't use 2. Your original asymptote was x equals 0. You added 2. Your new asymptote is x equals 2. Same way we did this before. It was usually on the exponents we never affected domain, right? Because domain was all real numbers. We didn't have an effect on the domain. We only had effect on the range. But this interchanges. So now the log gives us an effect on the domain and not the range. It's kind of a reverse thing going on. Okay? I'm going to give you your homework.